Hi guys, welcome to a lesson of partial differential equations. So in this class, we are going to discuss the solution of heat equation using Duhamel's principle. All right, so uh, we are dealing with the non-homogeneous heat equations of the form ut minus uxx is equals to some function of x and t. All right, so in this case, we discussed various methods to solve the problems. But now we are going to use another important method, that is Duhamel's principle for the partial differential equations. So if an equation is given in this form and the conditions are given as u of 0 comma t is equals to some function of time, and then u of L comma t is also some function of time, and then u of x comma 0, that is the initial condition, is some function of x. So now we know that the solution is given by u of x comma t is equals to wx comma t plus vx comma t. All right, so this wx comma t we can find by the formula, that is b of t minus a of t divided by L times x plus a of t, right? So we already know that we can find the solution using this equation. And then for vxt, we can use this equation to find uxt. If w of xt is found, then we can use this equation. So we can write in this form vt minus alpha squared, or let's say c squared if some constant is given, c squared vxx is equals to ut minus c squared uxx minus wt minus c squared wxx. So in this form, by using this form, we may get an equation of the form vt minus c squared vxx is equals to some function of x comma t, and then the boundary conditions may be transformed like this: u of 0 comma t is equals to 0, u of L comma t is equals to 0, and then u of not u, this is v and b. So v of 0 comma t and v of L comma t, and then v of x comma 0 is some function of x, right? So now for this equation, we can split this equation into two parts. All right. So in the first part, we can write it in this form: v is equals to v1 plus v2. So now the equations will be v1 times t minus v1 xx. Sorry, v1, this is not v1 times t, this is v1 subscript t. That is the derivative of v with respect to t. This will be equals to 0 with the boundary conditions. It remains v of 0 comma t is equals to 0, then v of L comma t is equals to 0, and then the boundary condition will be v of x comma 0 is equals to v of x comma 0 is equals to u of x comma 0 minus w of x comma 0. All right, this is we can say that this is first part, and then the second part will be v2 subscript t minus v2xx is equals to the non-homogeneous part, that is q of xt, and then these equations boundary conditions will be 0 here, it will be v1 v1 and then v1 v2 v2 L comma t is equals to 0, and then v2 of x comma 0 will be 0, right? Because this will be v2 is equals to v minus v1. So v is actually here, you can see that g of x, that is equals to u of x comma 0 minus w of x comma 0, right? So when we subtract this from v1, we will get zeros, right? So this will be always 0. So this is the second equation. And we know that the solution of this equation we can easily find. This is now homogeneous Dirichlet boundary conditions and homogeneous heat equation. So we can easily solve this problem. We already know the solution of this problem, but for this problem, say this is 2 and this is 1. So for 2, we are going to use the Duhamel's principle, right? So what is Duhamel's principle now? So the Duhamel's principle says that if an equation is given in this form, this equation 2, so we are going to convert the equation into Duhamel's form. So now 2 implies that nu t minus c squared nu xx is equals to 0. We are actually transforming this equation, right? And the boundary conditions will be 0. So we are not concerned with the boundary conditions in this equation. We only need the initial condition. So now the initial condition will be actually, we can see here this q of xt. So here it will be q of x comma s. All right, so we can write the initial condition in this way. And then we can solve the problem. Now the solution, that is v of x comma t, will be equals to integral 0 to t v of x comma t minus s such that s ds. All right, so we can find this vxt in this manner, and this will be actually v2. All right, this will be actually v2. So the particular solution will be u of xt is equals to w of xt plus v1 plus v2, because we already said that v is equals to v1 plus v2. So this will be the final solution, right? So let's take an example. Let's start with an example. Example 1. So consider that we have an equation ut minus c squared uxx is equals to t times sine x, and the boundary conditions are, this is a simple problem though, so it's t, this is t, right? And the initial condition is also 0. So now this equation is already in the form that we can apply the Duhamel's principle to this equation by transforming this equation to the Duhamel's form. So we can see that this equation is compatible with equation 2 that we solved earlier here. This equation, we can see that that equation is very much compatible to this non-homogeneous heat problem with the homogeneous boundary conditions and zero initial condition, right? So we can transform these equations to the Duhamel's form. So here with the Duhamel's form, v t minus c squared, sorry, this is not v, this is nu t minus c squared nu xx is equals to 0, and we are not concerned with the boundaries because they are 0 0. Then nu of x comma 0 such that s will be equals to s sine x, right? Because here it is t sine x, so this t will be equals to s. Because we are concerned with the function of s here, we can see that it's s, right? So now this will be s sine x. And now we know that uh, so we can see that there, here it is sine x. So we know that v x comma t such that x such that s would be a function of this form, because here we can see that this is x comma 0, but if we want the function of x and t and s, then it will be like this: s e to the power t, sorry, negative t sine x e to the power negative c square t, right? C square t, because we know that from the solution of heat equation we get the solution always in this form: e to the power negative n squared c squared uh, t over l squared, right? Instead we can write like this: e to the power negative n squared c squared pi squared t divided by l squared, right? With sine n pi x over l. All right, so here you know that L is equals to pi, so it will be to the power negative n squared c squared t times sine and x, right? And from this equation we can see this is sine x, so it means that n is equals to 1. So this will be now e to the power negative c squared t sine x, right? So this is the actual function that we need, that is v of x comma t such that s, and s will also be here because of this s, right? Now we can apply the Duhamel's rule, that is v of x comma t is equals to integral 0 to t v of nu of x comma t minus s such that s ds, right? So this will be 0 to t, and the function is s e to the power negative c squared t times sine x ds, and instead of t we should write t minus s, because in the formula it's t minus s, right? Here it's t minus s. So we can write in this way. This implies that we can bring this e to the power negative c squared t outside with sine x, and integral 0 to t s e to the power positive c squared s ds, right, in this way. So we can integrate this using the bypass rule. This implies that this will be to the power negative c squared t sine x s e to the power uh, c squared s divided by c squared minus e to the power c squared s over c raised to the power 4. And limits are from 0 to t. We will apply the limits. So it will be to the power negative c squared t sine x times t e to the power c squared t over c squared minus e to the power c squared t over c to the power 4, and then plus 1 over c to the power 4. All right. So now we can multiply this function inside, and we will get t sine x over c squared minus sine x over c to the power 4 plus e to the power negative c squared t sine x over c power 4. So this is the final answer for the given equation, right? So in this way we can work out the equation using the Duhamel's principle. Now we'll take one more example in which we can see that we will use Duhamel's principle, but with the new approach, right? We can see here now in the next example. So here is example number 2. heat equation is given, that is non-homogeneous heat equation. Alpha squared uxx is equals to t times sine 2 pi x plus 2x. All right, and the boundary conditions are also non-homogeneous this time. T squared, and the initial condition is also non-zero. So now we are going to work, and we are going to add some more steps in this problem. Unlike the previous problem where we directly solve using the Duhamel's principle. But now we are going to use the Duhamel's principle for this equation in a different way, right? So let's start this example. Now we know that the solution for this problem will be given by u of x comma t is equals to w of x comma t plus v of x comma t. We didn't work for this w of x comma t in the previous example because there the boundary conditions were 0, 0, and we know that w of x comma t is equals to b minus a over l times x plus a. So b is 0, a is 0, a is 0, so this will always be 0, right? That's why we didn't work out for this wxt in the previous example, but in this case the boundary conditions are non-homogeneous, so we are going to work out for w of x comma t. So here we can see that w of x comma t is equals to b minus a over l times x plus a, and b is t squared, so this is equals to t squared minus 1, l is equals to 1 times x plus a is 1, so this will be equals to t squared minus 1 times x plus 1. All right, so here we found w of x comma t, that is this function. Now for v, we know that this is equals to ut minus c squared uxx minus wt minus c squared wxx. So vt minus c squared vxx is equals to ut minus c squared uxx, which is given as this. All right, let's write it c squared. It doesn't matter if the constant it's alpha or c, right? So this is t times sine 2 pi x plus 2x. T times sine 2 pi x plus 2x minus. Now this wt, here we can work out for wt from this equation. This implies that wt will be equals to, we will differentiate this. So this will be 2tx, right? And then w of xx will be 0 because x the maximum power is 1 for x and the second derivative will be 0, right? So we can write 2tx, and the boundary conditions will be now v of 0 comma t will be 0, v of 1 comma t will be 0, and v of x comma 0 will be equals to u of x comma 0 minus w of x comma 0. So this is equals to this 2tx, and this 2x with t will cancel out, and we will only left with t sine 2 pi x. All right, so here we can write u of x comma 0. So u of x comma 0 is given as 1 plus sine pi x minus x, pi x minus x, and minus w of x comma 0. So w of x comma 0 will be negative x and positive 1. So we will only left with sine pi x. So v of x comma 0 is equals to sine pi x. So now we can see that the equation, the final equation is in this form. Vt minus c squared vxx is equals to t sine 2 pi x, v of 0 comma t is equals to 0, v of 1 comma t is equals to 0, and v of x comma 0 is equals to sine pi x. Now we need to split this equation because the initial condition is non-zero, so we need to split this equation in two parts, as we discussed earlier, that v is equals to v1 plus v2. The first equation will be v1 subscript t minus c squared v1 subscript xx is equals to 0 with homogeneous boundary conditions and with the initial condition sine pi x. And equation 2 will be v2 subscript t minus c squared v2 subscript xx is equals to t sine 2 pi x with homogeneous boundary conditions and with zero initial condition, right? So we can call it as 1 and this as 2. So 1, we can see that this is equation 1 is homogeneous heat equation with homogeneous Stricklet boundary conditions, right? So the solution for this equation we can write directly, that is, here we should write v1 and this is v1, this is v2 and v2, right? So v1 of x comma t, we can write it directly e to the power negative pi squared c squared t times sine pi x right? By using the initial condition, we can write the solution by inspection, right? And for 2, now we need to use that Duhamel's principle, right? Because equation 2 so is a non-homogeneous with homogeneous boundary conditions and initial condition, right? So now we can convert that equation to the Duhamel's uh, form, that is nu t minus c squared nu xx is equals to 0. We are not concerned with the boundary conditions here, so nu of x comma 0 such that s will be equals to, here we can see that this is t sine 2 pi x, so we can write s sine 2 pi x, s sine 2 pi x, right? But we need here the function with t such that s. So now we can see that here it is 2 pi. So n is equals to 2 pi, right? So we can write e to the power negative n square, that is 2 pi squared. So it will be negative 4 pi squared c squared t sine 2 pi x. All right. So now we can solve the equation for v x t. So v of xt is equals to integral 0 to t s times e to the power negative 4 pi squared c squared times t minus s sine 2 pi x ds. So we can take out the constants from the integral, so it will be e to the power negative 4 pi squared c squared t times sine 2 pi x integral 0 to t s e to the power 4 pi squared c squared s ds. Now we know how to integrate this function. We can use by part rule to find the solution of this function. So here it will be the power negative 4 pi squared c squared t times sine 2 pi x into s e to the power 4 pi squared c squared s divided by 4 pi squared c squared and minus e to the power 4 pi squared c squared s over 16 pi 4 c to the power 4 0 to t. Now we can apply the limits. Sine 2 pi x, this will be t to the power 4 pi square c square t divided by 4 pi square c square minus e to the power 4 pi squared c squared t divided by 16 pi to the power 4 c to the power 4 plus 1 over 16 pi to the power 4 c to the power 4. We will multiply this function to the bracket, so we will get sine 2 pi x is common everywhere. This multiplied by this one will be t over 4 pi squared c squared, then minus 1 over 16 pi to the power 4 c to the power 4 plus e to the power negative 4 pi squared c squared t divided by 16 pi to the power 4 c to the power 4, right? So this is our V2. Now we can write u of x comma t is equals to w of x comma t plus v of x comma t, where v of x comma t is equals to v1 plus v2. So in general, u of x comma t will be equals to t squared minus 1 times x plus 1 plus the solution for v1, which we found earlier, was e to the power negative pi squared c squared t sine pi x plus now v2 of x, right? So v2 of x comma t, sorry, it's this function, this one. So sine 2 pi x times sine 2 pi x times, that is t over 4 pi square c square minus 1 over 16 pi to the power 4 c to the power 4, and then plus e to the power negative 4 pi squared c squared t divided by 16 pi power 4 c power 4. So this is the final answer, and you can check the boundary conditions and the initial conditions for this equation. So the conditions must be satisfied by this equation, and also the solution should satisfy the equation, right? So in this way we can work out the problems using the Duhamel's principle. All right, so in the next class, we will discuss about some more methods for the heat equation, like the Laplace transforms and the eigenfunction expansions, right? So goodbye till then, and thanks for watching the lesson.